linear systems, things that we can model that work as a line. But we'll see from the very beginning that data doesn't really work perfectly with a line, but lines are so simple, they're easy for us to understand, that they're a great tool to predict the future, predict the past. If this worked perfectly as a line, this is what we would predict for the future. This is what we would have predicted the past to be. So these linear, just a line, and you can see that graph there. But you can also see that the data points don't land directly on it. Okay, so what is this? This is this is a model of the percent of time spent on cell phones daily. So this would be starting at 16% up to 60%. Okay, and then this is your anxiety level, or the people in the study, their anxiety level out of 100. So we can see that corresponding. So over here would be 50% of the day, and we can see, okay, well, this is there. How this was recorded, I don't know. It's a silly example, but that's the idea. That's the idea of the graph here. What this is a linear equation, and this is, you probably remember it from high school. This is y equals mx plus b, okay? So that's the same as what you learned in high school. All right, well, what do those letters mean? The y is the output, okay? In this case, that's anxiety level, okay? Okay, Aaron remembers it, and you probably hated it, but don't, this is a commonly hated thing because people remember it from high school, but it's really not that bad. Okay, so this is the output. This is where it's telling us the level of anxiety. All right. Now, all right. So everyone's upset in the chat there, but it's not that bad. It's not that bad. All right. This number here, this m, so y equals mx plus b. This is the slope. Okay, and the slope is the rate of change, how it changes with whatever the increments are. Here it's percent of time. It's often time with our class. Often as time goes on, something is changing. Maybe it's often it's money, maybe profits. It could be amount of people. That's common for our class. It's common for us to see how things change as time changes, okay? So that's important to keep note. But the slope here, this m, this is where the m comes in. This is the m. So the m is the slope, and the slope is the rate of change, how this thing is changing. So how is it changing? It's changing 2.1382. The thing we need to notice is that that's a positive number, okay? So it's changing positively, and that's what we see here. It's going from left to right, it's going up. That's positive, okay? Okay, so because of that positive change, as time goes up, that's generally what we study. As time goes, this is going up, okay? As time spent on the phone, this study is showing the anxiety goes up. Okay, that may be true. This is just a silly example. It could be penguins that sit out in the cold grow colder. I mean, we could, you could also do anything. You could make a graph of anything. But the thing I want you to notice is, what does that slope means? That's a quantitative number to represent the change that's going as the percent goes up. Okay. The x is what the input value is. So we have input, output. Okay, input, output. So in this case, we would be putting 40 in. Okay, if you input 40, you're going to get a number that's close to 66 out of this. Okay, so the x is the number that you're putting in the equation. And the b here, this is the b. This is the base. This is the starting value, okay? And I won't bore you with all the history of this. Well, we don't even have time for me to even say anything about it. But the history of this is kind of interesting, and where this comes from. Why are we using these particular letters? But you can think of this as like climbing a mountain. All right. That's kind of the inventor of this system. That's how he thought of it. So you're climbing a mountain. The base is where you started from. Okay. So you can imagine here's a poor drawing. Let's say this is the base. Okay. There could have been something below there, but here is your base, and you're climbing up. You're climbing upwards. Okay. Mountainous. It's actually, I don't know French, but maybe one of you does. I think one of you is studying French. It's to climb. There's the French word to climb, which is something like mountainous or something like that. That's where the M comes from. So it means to climb. How does this line climb? That's what it means. Okay. All right.
Montaigne.
What was it?
Montaigne
Montaigne means to climb.
means mountain.
Oh, it means mountain. Okay, this means to climb the mountain or something like that. That's what it. That's how it works. Okay, great. Now, let me get my. Too many buttons. Okay. So what is the slope of this model? Okay, in this model, the slope is 2.1382. That is what the slope is for this model. I am giving that number. It was given to me. I'm reporting that number. I did not have to calculate it in this example. It was given to me on the graph. The computer was given this data. Okay, it was giving these corresponding information, and it outputted this equation. You can do this in Excel. But in this, I'm just answering, this is what the slope is, just writing the number down, okay? Make a prediction for someone who's on the phone 50% of the day. How does this compare with the real value? So that's two questions. First question is, make a prediction for someone who's on the phone 50%. All right, I'm going to take this line away because I don't want to use that anymore. 50% of the time. Okay, so here's 50 right there. And I'm going up, 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 up. Okay. So it looks like the real value is 79. I don't know if you can see, I can't even see it that well, but there's like a little 79 there. So it looks like the real value, there's a 79 that corresponds to this dot here. The real value is 79. That's the real value. What is our prediction? Our prediction is putting the X number, this is the X axis, we're putting the X number in this equation, okay? So Y equals 2.1382 times 50 minus 20.898. Okay, so I need to input this into my calculator, and I'll find what the line predicts. Okay, so it said, make a prediction for someone who is on their phone 50% of the day. Take 50, okay, it looks like it's 79. That's the real value. What is the predicted value is me putting 50 in the equation that was given. Okay, so let's do that. 2.1382 times 50 minus 20.898. Okay. It doesn't tell me how to round, so it's 86.012. Okay, so I find roughly 86% is the predicted value. All right, the real value is 79. So we are determining both visually and using algebra that the predicted value is above the real value. We're predicting it to be above the real value, okay? And that happens with studies, okay? It's not perfect. Lines are not a perfect model of reality. And the more information we have, the closer our lines can get. but it's pretty good. It's pretty good, and it's easy to understand. So it's easy to report values, okay? But there is some error. So how does this compare with the real value? The real value in this problem is 79. Our predicted value is 86. So the prediction is above the real value. And that is something you will see on your homework. Is it above or below? That'll be something. Is it more or less? In this case, we would consider it to be above or more. That would be the same idea. The prediction is more than the real value. Okay, prediction is more than the real value. Okay, if someone had a max level anxiety of 100, what is the predicted percentage of the time on the cell phone? Now they're giving me the output value. They're giving me the output value. They say, what if it was 100? They're maxed out, 100%. Just 100% anxiety, okay? What is the predicted percent on their cell phone? So now we're solving for X. This is telling me to solve for X, all right? It's telling me the output. This is the out. It's saying solve for the input. That's what it's telling me. Okay, so that's what I'm trying to do. How am I going to do that? So I know what the output value is. It's 100. I know the equation of the line that's given to me in the problem. I have to somehow solve for that. So, okay, let's set up what we know. We know the equation of the line that was given, y equals this 2.1 minus 20. So we know that's true, okay? Y equals 2.1382 x minus 20.898. We're told what the output value was. Okay, the output, this is the 100. They're telling us that's 100. Okay, 100 equals 2.1382 times x minus 20.898. All right, how do we solve for x? How do we solve for x? The way we're going to do it is we need to subtract and then divide. Okay, well, what do you subtract and what do you divide? Since the 20.898 is being subtracted, oh, I'm sorry, we're going to need to add and then divide. So we need to add the 20.898 to the 100 since this is being subtracted, and then we need to divide the 2.1382. Okay, and this is order of operations that you learned in your algebra courses. Okay, maybe you took intro to algebra at Ivy Tech, but what we need to do is we need to add this number to both sides. Okay, we need to add the 20.898 to both sides. Then we're going to divide by this number, the slope, because it's being multiplied. All right, well, adding this number to 100 is very easy to do. Okay, so that's not a problem. So that'd be 120.898 divided by 2.1382. Okay, that's going to be our X value, the input value. That's what we're solving for. We're solving for the input in this question. So 120.898 divided by 2.1382, I'm finding would be roughly 50. Well, it doesn't tell us how to round, so we don't have to round very much because we can say with some certainty we know from the thousands. So 56.542. Okay. Okay, now I'm going to say this again. This is more important than even getting the solution, is understanding what I'm solving for. Okay. If you understand, I'm sorry for being so repetitive. I just want to make sure it's clear. In this problem, in the original problem, it said you have a max level of 100. What is the predicted percentage of the cell phone? So by the word predicted, I know I'm using the equation of the line. I'm not reporting the real value from the chart. Okay. So that's clear. They're giving me the output. Okay. This could be about ice cream profits. This could be about movie ticket sales. This could be about anything. Okay. It doesn't have to be cell phones and anxiety. This could be about anything. Okay. Anything you can dream of. But in this problem, they're giving you the output. We're solving for the input. How do you do that? Okay. You take the equation of the line, you put the output in its respective spot, which is the y. Okay, that's the output of the function. We're going to do the opposite, whatever the sign is. In this case, it was subtracting, so we have to add both sides. If it was the other way, we'd have to do the other thing. If it was positive, we would have had to subtract. Then we're going to divide. Okay, we're going to divide the slope. We will always divide the slope. Okay. In doing so, we find the input value. This is the input value. Okay. The input value that would make that true. All right. It's a lot. The good thing is we're going to do another example. So hopefully it will, hopefully it'll be okay. But it's a lot at first, especially because I'm also bringing up things you probably saw in high school and you have a negative opinion about. That's often what happens in high schools. Last question about that chart. Is this a positive or negative trend? What would it classify as strong, moderate, weak? The second question here is kind of an opinion, but we can justify that opinion. But the positive or negative is, it either is or it is not. This is by definition a positive. This is positive, okay? It's going from left to right. It's going up. It's going up. This is positive. Okay, that's positive. Okay. So I hope that's clear. This has to be positive. This is positive. If it was going the other way, if it was going down, that's negative. Or if the slope is negative, that's how you determine if it's negative. So you can determine it by the slope. Since this number is positive, the line is positive. Okay, so that's positive. It's going up. You can determine it visually, or you can just look at the slope if that's given. Okay, I hope that makes sense. And then, is this strong, moderate, or weak? This is kind of an opinion. If we look over here, I would say this is relatively strong. The data is roughly right on the trend line, right on the predicted line. If we go over here, like over here, it's weak. This is weak, all right? This is strong, okay? So the actual graph kind of has both. It kind of has strong points and weak points. So I'm just going to have to say that this is moderate, okay? This is kind of an opinion, but I would vote that this is moderate, okay? It has strong points where the data is almost right on the line, and it has weak points where it's way off, way off. So I would say this one is moderate, okay? And you'll see that on your homework and in the forthcoming exams. But you can fairly justify it, all right? Hopefully on an exam, it would be definitely one or the other, okay? What is the slope of this model? Write a meaningful sentence about it. Okay, this is a whole new graph. What is it? Weeks after the start of the year. Okay, so that's how time is ticking. These are weeks. So the X is in weeks. All right, what's over here? The output is the percent of people who exercise daily. Okay. So what is the slope? This is the slope. Okay. I should mention that the slope is the number and not the X. The X is the input. The number attached to that, its coefficient, that is the slope. The slope is negative 1.4518. Okay, that is the slope of this line. Okay, it's given to me as y equals mx plus b, where m is the slope. This is negative, it's going down. B is the base, that's its starting position. Okay, so the slope is negative 1.4518. Nothing magic about that. Write a meaningful sentence about this. Okay, what am I going to say? Well, as the weeks go on, the amount goes down, the output goes down. What is the output? It's the percent of people who exercise daily. So as time goes, as the weeks tick on, the amount of people that exercise daily is going down. Okay. So I would assume that this is something to do with the beginning of a year, right? Where maybe everyone's starting a new exercise routine, and then as the year goes on, it goes down. Okay, that's what this data is showing. All right. So as weeks increase, the percent of people who exercise daily decreases. Okay, so as time goes on, as time increases, the amount of people that are exercising decreases. That's what this is telling me. That's what it means. That's writing it in a meaningful sentence. Okay, increase, decrease. That's what we're really looking for. That the amount of people are decreasing. Okay, and that the amount of weeks that's going on, that signifies that you understand what the unit of time is. Okay. Make a prediction for week 30. Okay, well, week 30 is here, and that's right there. I want to make the prediction. Okay, I don't even know what the real value is, but I know the real value is roughly there. Okay, so I need to make a prediction. How do I make a prediction? I plug it into the equation. What do I plug into the equation? I plug in the amount of weeks. So this is the input, and I'm going to put the input into the equation and then solve what the output is. Okay, so let's do that. Y equals negative 1.4518 times 30 plus 98.396. I need to plug this into my calculator, and then I'll see what the predicted value is. Okay, that doesn't tell me what the real value is. That tells me what the trend line would say it is. Okay, I have to remember how to do negative numbers on this. I think I did it. 1.4518 times 30, okay, plus 98.396. All right, 54.842. 54.842 is the predicted percent of people who are exercising daily. Almost over 50%. Okay. Second part is the prediction above or below the actual data point? Is it above or below? The prediction is below. The prediction is below the actual data point. It's below. This is below. Okay, it's below the actual data point. How much? Well, that's kind of a guess for me. I don't know if you can see this zooming in, but hopefully you can see. If we look over here, it's not quite, and we just have to make an estimation because this isn't told to us. We can see that the actual data point is above that line there, which I think is 60. We can take a look at that. So the actual line is 60. We see that the actual data point is above that. So I'd say that's 61 or 62, something like that. We have to kind of estimate that. Okay, so how much is it above? I would say it is, I don't know, 61 minus 54.842. It's about 6 points above. Maybe I'll write approximately 6 points above. Okay, about. Okay, it's an estimation, but we can predict it. Okay. In what week is the percent of people who exercise 50%? In this, they're telling me the output. In this problem, they're telling me the output. Okay, how did we do that? If they tell them, well, maybe I should even go back further. How do I know that that's what's happening? In what week is the percent of people who exercise 50%? So they're not giving me the weeks, they're giving me the percent. So they're saying 50. Okay, so by the trend line, looks like it's somewhere between 30 and 35. That's a real rough guess, but they're giving me 50%. Okay, so how do I solve for that? Well, y equals negative 1.4518x plus 98.396. This equation is given to me in the problem. They're telling me if it's 50%, what is the input? How many weeks is that? Okay, so I need to put that 50 there. So I put 50 equals negative 1.4518 times x plus 98.396. Now I need to solve. How do I solve for something like this? Okay, how do I solve for something like this? In this case, this is being added. So I have to do the opposite. So I have to subtract. So I have to go 50 minus this 98. And then I'll divide by the slope. Okay. So I need to subtract it. Okay, so how do I do that? X equals 50 minus this 98.396 divided by negative 1.4518. Right? All right, 50 minus 98.396 divided by negative 1.4518. And did it tell me how to round? Not really. What can I say with any confidence? Looks like I could confidently say by the 10th. So that's 33.3. Okay, and that's what we roughly predicted by just looking at the graph over here, that it was somewhere between 30 and 35 that should land. We weren't quite sure where. Here we just quantified it. Okay, how did I do that? Okay, I'm sorry for all the zooming, and that's probably disorienting to see someone zoom like that. So I apologize. I wouldn't like it, but then again, I have to do it. So I apologize. All right. They're saying what percent of people, or in what week? In what week? We're solving for weeks. Solve for weeks. They're telling us the output. How do you do that? Plug your output in. We have to solve for the x. How do we do that? Okay. So here we have to do the opposite of what this is doing. So this was adding, so we have to subtract. So it's going to be 50 minus this 98.396. Then we divide. We'll always divide by the slope. Okay, so that's how we're going to actually calculate this. I want to take this circle away. We don't need it. Okay, so that's where I got the x. 50 minus the 98. Because this is addition, we need to use subtraction. Then we need to divide. And the reason we have to do it in that order too. I can't go 50 divided by negative 1.45 and then subtract. It would be different. That would be wrong order of operations. Okay. Okay. Can you predict what will happen 10 weeks into the next year? Okay. Can I predict what will happen 10 weeks? This is a little bit of a trick question. So I apologize for that, but I stole it from the book. This is the kind of language you'd see. 10 weeks into the next year. Okay, well, it's kind of tricky. So what they mean is 10 years after this point. Okay, a year has 52 weeks, right? So they mean 10 weeks after that. All right, well, how many weeks is that? They told me 10 weeks after. If there's 52 in a year, this is 52 plus 10, which is 62. So what would you predict at week 62? All right, y equals negative 1.4518 times 62 plus 98.396. Nothing, no tricks or anything on this one. We can just go straight forward. So how do we do that? We have negative 1.4518 times 62 plus 98.396. I'm finding about 8%, 8.3844 of those people would still be continuing with their program. Okay, so it's probably a lot to get a hold of at first, but the good thing is it's very repetitive. This stuff is very repetitive. It's generally the same questions over and over, except you just have different stories attached to it. In this one, it was exercise with weeks. Okay. Okay. Now in this, it says, in this example, well, just for time reasons, I want to skip ahead, but I can't. So section 8, part 2 discusses how to create a model without computer assistance. Problems can still be solved with the usual way of predictions, although no discussion about the correlation is necessary. Doesn't make sense without the graph to look at. The slope is still a number that describes the rate of change in the y-intercept. The y-intercept was the base. It's still a number that describes the start of the problem. General hint. X numbers are usually the count the things or times. Okay, that is key. Your X is usually time. Y values are usually money. Okay, usually, even outside of this class, usually they're money. Y numbers deal with money or profit. Sometimes it's amount of people, like we saw before. But often it's money. All right. Here's a nice example. I'm just going to skip to that example and just go straight to the problems for time's sake. So for every minute you spend with a math tutor, your grade tends to improve by 0.15%. If you spend 2 hours with a tutor, how much will your grade improve if your original grade was at a 65? Okay. So this almost sounds like a percent change problem. So we have to be a little careful with that. Through context, we know it's a line, but it kind of sounds like that. All right. So it says 2 hours. All right. But it also says every minute. So that's kind of confusing. So this is in minutes and this is in hours. And that's a little confusing. So because this is in hours and our grade changes every minute, so we have to be a little careful, but 2 hours is 120 minutes. I think that's clear. It's 2 times 60. That's fine. Okay, so we're spending 120 minutes with this tutor, and our grade improves 0.15 each minute. Each minute it increases. So how much does it increase? Well, it's 15 times this 12 over here. So that's what I'm going to do. 15 by 12. Okay, what's that? 150 plus 30 is 180. So our grade has increased 18%. Okay, I just multiplied those numbers. 0.15 times 120 is 18. Okay, it increases. Our grade was 65. It's increased 18. So that's 65 plus 18. 83%. Our new grade is 83%. Okay, this is the final grade. So our grade was increasing 15% each time. We spent 2 hours with them. That's 120 minutes. I just multiplied them and then added it. Okay, so this is a line. The 12, this, I didn't really explain that. Thank you, Michaela. So I was just trying to do the arithmetic in my head. The 12 came from 120 and the 15 just came from 0.15. So I was just doing the arithmetic in my head. That's how I got 15 times 20. So I was just trying to figure out how to calculate it. So you get 180 and I convert that back to 18%, but you can just use a calculator. Okay. A company's, I was just calculating it by hand. You can go 120 times 0.15. That's fine. I didn't mean to complicate it by the arithmetic. That was just a trick. Just moving the decimal is just a trick to be able to calculate it by hand. A company spent 1.2 million on supplies for their business. Every day they make an average profit of $10,910. How much profit will they have after 60 days? How many days go by until they break even? Okay, well, that's a few questions, so we need to take it piece by piece. They spent 1.2 million. They make a profit of $10,910 a day, and we want to know how many they make in 60 days. So there's almost 3 questions here. Y equals 10,910 x. I'm going to have by days. My y-intercept is going to be this 1.2 million, but they spent that. So they're kind of in debt. Well, they are in debt for that. So this is minus. Okay, so this is my equation of the line. Now it says how much will it be after 60 days? For this, I would just plug in 60. So 10,910 times 60. It's 1,200,000. Okay, just plug that in calculator. Times 60 minus 1. We're still getting a negative number here, so they're still in debt. Even after all that. Okay. So they're still in debt, but that answers after 60 days. Now, how many days go by they break even? This is something we see a lot in the textbook of this break even value. Break even means y equals 0. This is when there's no debt, okay? Also, if they mention in the problem break even, that's kind of a hint that there's some kind of debt in the problem, all right? But the break even means down to 0, okay? So 0 equals 10,910 x minus our 1.2 million. Okay. Now, how am I going to solve for something like this? This is being subtracted, which means I need to add. Okay. Once I do that, I have 1.2 million equals 10,910 times x. I need to divide. Okay, so let's do that. Whoops. Divided by. I'm getting 100, pretty much 110 days. So I'm getting, I don't see any reason to not just round to the nearest day. I think I'm going to, so this is just roughly x equals 110 days. Okay. That's how we would get that, all right? Now, I know this is a little weird of setting that equal to 0. This is to find the break even point, okay? That's the break even point, okay? So if you see something like break even, that's where you're setting the y equal to 0, and then you're going to solve for what the input value, the x is, all right? Did the opposite, this was subtract, so I have to add both sides, and then I divide by the slope, okay? That's the method. Method to the madness. All right, in these examples, we have to find the slope ourselves, okay? And this is going to be new minus old over new minus old, all right? So it's absolute change. New minus old, new minus old, okay? I didn't pick out these examples, but we're just going to go with them. So the game, The Legend of Zelda, started in 1986 with only one game. By the year 2019, 19 games in the series have been created. Construct a linear model to predict the number of games in the year 2050, round to the thousands. Okay, so we need to find the slope first. So let us do that. The new minus old up top, the numerator, is going to be the amount of games. So 19 games minus 1 game, 1986, okay. 2019 minus 1986, I'm going to subtract that to find how much time had passed. Well, 19 minus 1, it's just 18. How many is that? 4. And then not quite, so that'd be 33. So this is 18 over 33, and I could reduce that with 3's. $11. Yeah, that's our slope. So this is our slope. This is m. Okay. Now, where did it start? It started with one game. Okay. It started all with one game. So y equals 6 over 11 times x plus 1 game. Or you could convert this into a decimal if you like. And that would be rough. It's like 0.54 repeating. says round to the nearest thousand, so that would be fine. 0.545x plus 1. Both of those are fine. Both of those are fine. This one makes a little bit of an approximation, but both of those are fine. All right, so we've made our model. Great. Now it says use that model to predict the year 2050. Okay, 2050. Well, how many years after 1986 is 2050? That's what I have to find. 1986. So let's figure that out. That's 4 and 10 and 5. That's 64 years. Okay, I'll plug this in my model. Y equals 0.545 times 64 plus 1. This is what I would predict the amount of Zelda games in the year 2050. Okay. Times 64 plus 1. Rounding to the nearest game, it would be 36. But this problem is saying I need to round to the nearest thousand. So 35.909 games. Roughly 36 games would be my guess. Roughly 36 games. Okay, what did we just do? We're told how many games there were in 1986. We're told how many games were in 2019. We're trying to find how many games there will be in 2050. We had to find the slope. So find slope. Okay, that's what we did. 19 games minus 1 game over the amount of years that passed. 18 over 33, which we found to be 0.545, plus the 1 game we started with in 1986. They asked us to predict the year 2050. Okay, I have to find how many years past 1986. That's where I'm coming up with that 64. 64 is plugged in. Here's my slope. I add 1. I'm coming up with about 36 games in 2050. Okay, I guess we'll see if that's right, but that's the idea. Okay, so in that one we had to find the slope. The next one I think is roughly the same question, but with different specifics. So this one is James Bond. James Bond movie franchise spans over 50 years in business. In 1980, there were 11 movies. In 1990, there were 17 movies. If the trend continues, how many would there be in 2020? Or what would this have predicted there to have been in 2020? So we need to find the slope. Okay, how do I do that? M equals, and I want to take the difference of the movies. So that's 17 minus 11. And then the difference in time was 1990 minus 1980. Okay. 17 minus 11, I suppose, would be 6. And this would be 10 years. And that would be 3/5. So I think that's my slope. My slope is 3/5. Okay. Now we need to make our model. Y equals 3/5 x plus, here we're starting with 11. So I can go plus 11. Okay. Not too bad. If you want, you can turn 3/5 into a decimal. That's up to you. That's 0.6. That's fine with me. Okay. They want us to predict how many movies there would be. If this held true, how many would there have been in 2020? Okay. Well, how much time had passed between 1980 and 2020? We need to find out. 2020 minus 1980, and that's 40 years. Okay, so I think 40 years had passed. So y equals 0.6 times 40 plus 11. Okay. Awesome. 0.6 times 40 plus 11 is 35. Y equals 35 movies in the year 2020. I don't know how many there was, it doesn't matter, but this is how you would calculate it. Okay.